Okay, we talked about the RNS stereochemistry, which gave us enantiomers. But let's talk about E and Z and their stereomers too. So now, assume you have alkenes, okay? If the alkenes has only carbons and hydrogens, like this one, if you cut across, you'll see that the big group, the CH3s on the same side, we call these Cs. If the CH3 or B groups are opposite when you cut across the double bond, okay, so you see here, CH3 is up, here CH3 is down, we call this trans. But whenever we have other elements on the double bond other than hydrogen and carbon, we have to use a different system for isomerism. So we use E and Z. So for example here, you have halogens and sulfur. Those are different from hydrogen and carbon, so we don't use cis trans, we use E and Z. E we refer to opposite, Z we refer to same side. So we use the same Kern-Ingold rules to assign priority. The first step you want to do is to cut the double bond across and then use atomic number to assign priorities. So let me find my periodic table. Alright, bromine has atomic number 35. Okay, that has atomic number 35. Iodine has atomic number 53. Okay. Chlorine has atomic number 17. Sulfur has atomic number 16. Now that we know the atomic numbers, we can assign priorities on one side than the other side. So since iodine has a higher atomic number than bromine on the right side, iodine will get priority 1, and then bromine will get priority 2 on the right side. Then come to the left side. Chlorine has a higher atomic number than sulfur, so chlorine will get atomic number 1, sulfur will get atomic number 2. Notice that I'm assigning priorities to groups directly attached to the sp2 carbons. I don't care about the hydrogen. I'm just caring about the sulfur, chlorine, iodine, and bromine. Cut it across, assign priorities based on atomic numbers on each side. So in this case, the high priorities are on the same side, so I should call this Z isomer. Okay. Same here. I'll cut the double bond across. Bromine has atomic number 35. Chlorine has atomic number 17. So bromine gets priority 1. Okay. Based on the atomic number, bromine gets priority 1. Here, unfortunately, you have a carbon and a carbon attached directly to the ring. So you use the Kern-Ingold rules that we said whenever there's a tie in atoms directly bonded to the chiral center, you move forward. So like here, this carbon moving forward is bonded to 2 hydrogens and the carbon. So I'll list the carbon first and then the 2 hydrogens. This carbon here is this one here. I'm looking at what's bonded to it moving forward. I don't go back to the chiral carbon. And then this one moving forward, I'll have 3 hydrogens. So obviously, there's a tiebreaker here. This carbon wins over the hydrogen. So the ethyl group gets priority 1 over the methyl group, which will get priority 2. So this time, the priority 1s are opposite, so this is called the E isomer. So that's the process. And of course, that's what's being explained here. So this, we found out that the high priorities will be these ones. So the first priority is on the same side, but they're together, so we call this Z isomer. Here, high priority is on the opposite side, so we call this E antigen, which means opposite according to these two German words. That's where the Z and E comes from. Okay. Now, what about what we call Fischer projections? These are very important, especially in biochemistry. You'll find that sugars are drawn as Fischer projections. Okay. So instead of drawing what we call the Sohos, remember we've been drawing something like, let's say you have this structure. This would be the Sohos. Instead of drawing the Sohos, probably you can define the stereochemistry. One will draw a straight line, or a vertical line, sorry, where the tail and the heads will be at the polar ends. So, and then these OHs, okay, will be on horizontal line. You know, there's a hydrogen here. There's a hydrogen here. So those ones will be on horizontal line. Okay, so this is just an example to show you that Fischer projections will be drawn using vertical and horizontal lines. It's just a translation of what we call the Sohos drawing or projection to what we call the Fischer, which uses horizontal and vertical lines. Okay. So examples are these. So you see, the rules are any group that's at the polar end will bear the dashed lines, which means away. And any group that's on horizontal will bear the towards bond. So these dashed lines or dash hatched bond means away. Any horizontal groups will bear the shaded wedge, which means towards. Now, if you put a mirror in front of this structure, this is what you're gonna see as an image. Okay. Same applies here. There's another Fischer. Put a mirror in front of this original image, original Fischer drawing. You're gonna see this image. Same here. Put a mirror in front of this original Fischer drawing. You're gonna see this image. Now let me say something about what we have here. You see how we have two carbons in between. So the bonds that are in between will be just a typical straight line. So if I had 3 carbons, okay, so if I had 3 carbons, those lines in between will be typical straight line. Okay, and then the ones at the end will bear the dash bond. So let's say you have these groups A, B, C, D, E, and F. So only the head and tail will bear the away hatched bond. Anything in between will be a straight line. So that's why we have a straight line here. And then the last 2 bonds will bear the hatched or away bond, away wedge bond. Okay. Remember we said the broken bond means away from you. Then the vertical lines will be towards you, just like a butterfly with its wings upwards. So anyway, put this in front of a mirror. This is what you're gonna see. These are the CH3s right here. CH3, CH3, which will be the image of that. Okay, so again, that's the original. This is the image. So Fischer projections can have their mirror images. Then what will be left to define is whether they are diastereomers, enantiomers, or meso compounds. So if you exchange any 2 groups, you're going to change the configurations. 3 groups can be rotated by any amount of degrees because sigma bonds can be rotated can be rotated. For example, if I rotate this bond, so let's say we call this A, B, and C. If I rotate that bond of the Fischer projection, then I'm gonna get C on the left, B here, and then probably A will stay there. So you will have rotated three groups in 3D. So of course the A was away, so here it's gonna be towards you. So what I'm saying is that you can use a sigma bond to rotate the rest of the bonds. Okay. Now if we rotate the entire diagram by 180, you're gonna invert the configuration. So which means if you have an original image, okay, and then put it in front of a mirror. So if this was S, and then you put a plane of symmetry or a mirror, then the image will have an R, for example, configuration. So rotation of finding the mirror image of the original will invert the configuration. So now let's explain what you're saying here, because this is just too complex if we don't use examples. So let's assign chirality and see. So let's use specific examples to explain this slide. So let's say you have this molecule. Let me redraw it for clarity. So there's a carbon in the middle, and then there's OH, and then there is H, and then there is CH2. Of course, there's an oxygen and a H. So if I am to assign priorities based on Kern-Ingold rules, the hydrogen on this, of course this is a chiral carbon, you have 4 different groups. The hydrogen on this carbon will get priority 4. It has the smallest atomic number. Oxygen is directly attached to this carbon in question, so we get to give it priority 1. And then between this carbon and that carbon, this one is bonded to, doubly bonded to an oxygen, so we pretend it's bonded to 2 oxygens like we said earlier. This is only bonded to 1 oxygen, so this is heavier, so to speak, so this gets priority 2 and this gets priority 3. So right now our smallest group is towards us. Do we want that? No. So for temporarily we're gonna assign chirality, and because this is the smallest group is towards us, we'll switch the answer because we want it to be away from us. So this is counterclockwise and we call it S configuration, but it's only S. It's S when H is towards us. It's S when the smallest group, number 4, is towards us. But to assign the true chirality, the H must be away from us. So the opposite of towards is away, which means the opposite of S is R. So the true assignment here is R. So the chirality of this carbon center is an R. What about here? Okay. So again, this group 4, we say that the aldehyde will be 2, oxygen will be 1, and this will be 3. So this time we are going 1, 2, 3. So we are going clockwise, like the way your hand clock will go. So this will be R. It's R when H, the smallest group, is towards you. How do I know it's towards? Because this bond is shaded wedge. But the true assignment should be given when the smallest group is away. So you just switch the R to an S, which would be truly your answer. So now you see, whenever you put a molecule, an original molecule, in front of a mirror, the chirality is inverted. And that's what this point says right here. If you exchange any of 2 groups, you're gonna invert the configuration. So whenever you put a molecule in front of a mirror, what you're really doing is you're exchanging two groups. You see here the hydrogen was on the right, OH is on the left. You see the hydrogen here is on the left, OH is on the right. So you've exchanged, because now here the OH is on the left, hydrogen is on the right. You've exchanged two groups, and that leads to inversion of configuration. All right. So if you don't show the 3D wedges, you're gonna see that, and you're going to see that. It's the same molecule, only not showing the wedges. Okay. Same applies to what we have here. Let's try and assign chirality. So this time I'm going to use this to assign. We know that if it's drawn like this, all vertical lines should be towards, and the polar bonds should be away. So let's pay attention a little bit here and assign chirality to the original image. All right, so hydrogen will get priority 4. I'm looking and focusing on this carbon because it has 4 different groups. You see CH3, OH, and H, and the entire rest of the structure is different. So this carbon right here is chiral. Okay, hydrogen will get priority 4. Has the smallest atomic number of all. Oxygen has atomic number 8 compared to this and this carbon, which are surrounding this marked carbon than asterisk. The 2 carbons have an atomic number 6. So how do we assign who gets priority, this carbon or this carbon? Obviously this carbon is more substituted than that, whereby you have few hydrogens here than that. So by eyeball, I'll know that this carbon right here will get priority 2. This will get priority 3. So going with numbers, I have 2, 1, 3. I'm not including the 4 because we assume it should be the other way. But remember, because these 2 groups are vertical, so the bonds used is towards you. So whenever the smallest group is towards, the chirality or the RS assignment is an R. You're going clockwise. But the smallest group is towards us, so the true assignment is an S, because before you assign the final answer like we did here, you have to make sure that the smallest group is away from you. Here it's towards us. It's on the vertical line, it's towards us. When it's towards us, it's an R. So which means when it's switched to be away, based on orientation or configuration, it should be an S. So let's work on the next one. So I'm going to redraw the molecule up here so we can assign chirality separately, and this is what you need to do on your worksheet whenever you're answering such a problem. So this time we already assigned this one to be an S. Okay, so now we have to assign this one, this carbon. So around this carbon, hydrogen gets priority 4, oxygen priority 1 because it has the atomic number of the 2 carbons and the hydrogen. And then this carbon here is more substituted than the CH3, which means it has few hydrogens than the CH3. That's one way to know. So you will take it to have the second priority because you have priority 1, and then this will be priority 3. Our numbers are going 1, 2, 3. So we are going R. We are going clockwise. It's clockwise when the smallest group, hydrogen, is towards us. See, it's towards us. I'm working on this carbon right here. So it's R when the hydrogen is towards us. So which means when it's away, it should be an S. So the true assignment is S. Now, if you do assign chirality on this one, you'll find that the chirality here will be an R, and here will be an R, where you'll have switched SS to RR. What do you call such molecules? Such molecules are said to be enantiomers, where you're switching chirality. So like these 2 guys are enantiomers. You have your R and S. There's no internal plane of symmetry. So where you have R switched to S, like I said before, when you're doing examples, you have enantiomers. Remember, enantiomers are non-superposable mirror images, okay, which don't have internal plane of symmetry. There's no internal plane of symmetry whichever way you cut the molecule. Next, we talk about the stereomers.